Imagine, if you will, a universe without our sun. It's a cold, dark thought, isn't it? Our sun is not just a bright light in the sky. It is the very heart of our solar system. From the warmth on your skin to the food on your plate, it all comes back to the sun. This magnificent star provides the energy that fuels life on Earth. Without it, our vibrant blue planet would be a frozen, lifeless rock, hurtling through the vast emptiness of space. The sun's influence extends far beyond just light and heat. Its immense gravity holds our entire solar system together. Think of it as a cosmic shepherd, gently guiding its flock of planets, moons, asteroids, and comets in their orbital dance. Earth, Mars, Jupiter, all of them are tethered to the sun by this invisible force. If the sun were to suddenly disappear, this gravitational grip would vanish. The planets would fly off in straight lines like stones released from a sling, venturing into the cold, dark, unknown. For millennia, humans have looked up at the sun with awe and wonder. Ancient civilizations worshipped it as a god, recognizing its life-giving power. Let's embark on this thought experiment, not to scare ourselves, but to appreciate the sheer cosmic forces at play. So, what exactly is this giant ball of fire we call the sun? It's not actually burning in the way a log fire burns. The sun is a colossal sphere of incredibly hot gas, mostly hydrogen and helium. It's so massive that its own gravity tries to crush it inward. This immense gravitational pressure creates unimaginable conditions at its core. We're talking temperatures of about 27 million degrees Fahrenheit, or 15 million degrees Celsius. Deep within this superheated core, something amazing happens. It's called nuclear fusion. Under the extreme pressure and temperature, hydrogen atoms, the simplest and most abundant element in the universe, are squeezed together. They fuse to form helium atoms. This process isn't just a simple combination, it releases a tremendous amount of energy. It's this energy, born from the transformation of matter itself, that powers the sun. This energy, born in the core as gamma rays and neutrinos, doesn't just pop out instantly. It begins a long journey outwards. First, it travels through the radiative zone. Here, photons or particles of light are absorbed and re-emitted by atoms, slowly zigzagging their way toward the surface. This journey can take hundreds of thousands of years. Finally, this energy reaches the photosphere, which is the visible surface of the sun. Now let's get to the explosive part. What would it mean for the sun to explode? Stars do explode. We call these events supernovae. They are some of the most violent and energetic phenomena in the universe. A supernova can briefly outshine an entire galaxy, releasing more energy in moments than our sun will in its entire 10 billion-year lifespan. However, there's a catch. Our sun is not the right kind of star to go supernova. Supernovae happen to stars much more massive than our sun, typically at least 8 times the mass. These giant stars live fast and die young, but for the sake of our thought experiment, let's imagine our sun explode in such a spectacular fashion. If the sun were to detonate like a massive supernova, the release of energy would be almost instantaneous and utterly devastating. The sun, our life giver, would become an agent of total annihilation in this hypothetical scenario. If the sun were to explode, we wouldn't know about it instantly. Light, even though it's the fastest thing in the universe, still takes time to travel. The sun is about 93 million miles, or 150 million kilometers, away from Earth. Light travels at approximately 186,282 miles per second, or 299,792 kilometers per second. So, if you do the math, it takes sunlight about 8 minutes and 20 seconds to reach Earth. This means that for a little over 8 minutes after the sun exploded, we'd be blissfully unaware, enjoying a perfectly normal day. Then, the sky would change. The first sign would be an unimaginable flash of light, far brighter than anything ever witnessed. This intense radiation, gamma rays, X-rays, and extreme ultraviolet light would hit the Earth's atmosphere first. Our protective magnetic field and atmosphere, which shield us from normal solar radiation, would be instantly overwhelmed. Immediately following this wave of lethal radiation would be an equally devastating wave of heat. The surface of the Earth facing the sun would be superheated to thousands of degrees in seconds. Oceans would boil away instantly, turning into superheated steam. Rocks would melt. The very crust of the planet would begin to vaporize. It would be the ultimate final end for our world as we know it. The devastation wouldn't stop with Earth. An exploding sun would wreak havoc throughout the entire solar system. The inner planets, Mercury and Venus being closer to the Sun, would be engulfed and obliterated even more quickly and completely than Earth. Mars, the next planet out, would suffer a similar fate, its thin atmosphere and frozen plains vaporized by the intense heat and radiation. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are much farther away and much more massive. They might fare slightly better initially, in terms of not being instantly vaporized. However, their thick atmospheres would be violently stripped away by the blast wave and intense radiation. The asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Neptune, home to countless icy bodies and dwarf planets like Pluto, would also be thrown into disarray. Our solar system, as a coherent, life-supporting entity, would be gone forever. Our Sun is truly a remarkable object even without imagining it exploding. For instance, did you know it accounts for about 99.86% of the total mass of our entire solar system? This immense mass is what gives the Sun its powerful gravitational pull, keeping everything in orbit. The Sun isn't static, it's a dynamic, active star. It has an 11-year cycle of activity, during which the number of sunspots, solar flares, and coronal mass ejections, or CMEs, increases and decreases. Solar flares are sudden, intense bursts of radiation, while CMEs are giant eruptions of plasma and magnetic fields from the Sun's corona. These mini-explosions can send charged particles hurtling towards Earth, sometimes causing beautiful auroras, the northern and southern lights, but also potentially disrupting satellites and power grids. Scientists use specialized telescopes with filters to observe the Sun safely. Some telescopes are on the ground, while others, like NASA's Solar Dynamics Observatory or SDO or the Parker Solar Probe, are in space. The Parker Solar Probe is actually touching the Sun, flying through its outer atmosphere, the corona, to gather data about how the Sun works. Now, after all this talk of cosmic doom and fiery explosions, you might be feeling a little anxious. So, let me reassure you. The scenario of our Sun suddenly exploding is purely hypothetical. It's a great way to explore extreme physics and appreciate our star. But it's not something that's going to happen. Our Sun is a very stable, middle-aged star, currently in the prime of its life. It's been steadily shining for about 4.6 billion years, and it has enough hydrogen fuel in its core to keep going for about another 5 billion years. As I mentioned earlier, our Sun simply isn't massive enough to explode as a supernova. It's a G-type main sequence star, sometimes called a yellow dwarf, though it's actually white. Stars that go supernova are cosmic behemoths, at least 8 times more massive than our Sun. Our Sun is destined for a different, much less violent end. In about 5 billion years, the Sun will become a red giant. Its outer layers will swell so much that they might engulf Mercury, Venus, and possibly even Earth. After this red giant phase, the Sun will shed its outer layers, creating a beautiful planetary nebula, a glowing cloud of gas. What's left behind will be its hot, dense core, a stellar remnant called a white dwarf, so sleep well tonight. The Sun will rise again tomorrow, just as it always has.